The limits of my language mean the limits of my world.
Ludwig Wittgenstein, 1922.
It's a bit of a heavy way to start a deep dive, isn't it? I mean, usually we kick things off with a weird tech anecdote.
It sounds philosophical, but I actually think it's incredibly practical.
How so?
Well, the quote basically says if you don't have the words for something, you can't really think about it. You can't work with it. And in software, that gets very, very literal.
Right. How we choose to structure our data. It literally sets the boundaries for what an application can or cannot do.
Exactly. And that is our mission for this deep dive. We're digging into the great debate between the different philosophies of organizing information.
We're not just comparing database features, which one is faster. This is about how we think about problems.
It's a real battle of ideas. You've got the reigning champion, the relational model.
Good old SQL. Tables and rows.
Then there's the challenger, the document model, which most people just call NoSQL.
And the third one, the kind of specialist in the corner, the graph model.
Yeah, the one that looks like a spider web.
And I want to be clear, this isn't just for database admins. This matters for anyone building software, right?
Oh, absolutely. Because picking the wrong data model, it's like trying to write a novel using only numbers. The language itself fights you at every turn.
Your development gets slower, the code gets buggier.
And eventually you hit a wall. You just can't build the feature you need to build.
So let's set the scene. Most apps are really just layers of these models.
Right. It's an abstraction stack.
Yeah.
Way down at the bottom, you've got electrical currents and you've got bytes on a disk. But the layer we're interested in today is that middle one.
The data storage layer, where you have to make a choice. Is my data a table, a tree, a network?
And for the last, 30, maybe even 40 years, the answer has almost always been
It's table.
the relational model. Edgar Codd, 1970. It has been the absolute king.
Which is just wild to me. 1970 is prehistoric in tech. That's the punch card era. Why did it last so long?
Because it was perfect for the biggest problem of its time. Business data processing.
Payroll, banking, airline reservations, that kind of stuff.
Exactly. Things that need to be rigid, structured. You need absolute certainty that the data is consistent.
Boring, but, essential.
Totally. And the genius of SQL was that it generalized incredibly well. When the internet came along with blogs and e-commerce, SQL was flexible enough to power almost all of it. It just became the default.
But then the cracks started to show. And this is where the source material brings up this amazing term, the impedance mismatch.
Yeah, it's borrowed from electronics.
So break that down for us. What does that mean in software?
Okay, so in electronics, if you connect two circuits with different impedance, you lose power. The signal gets messy. In software, the mismatch is between your application code and your database.
Because modern code is all object-oriented, Java, Python.
Right. In your code, you think in objects. You have a user object. And that user has a list of hobbies, a list of addresses. It's a nice, neat hierarchy. It's all self-contained.
But a relational database?
Hates hierarchy. It hates nesting. It only understands flat tables, rows and columns.
The square peg in a flat hole.
Exactly. And the resume example they use in the research is just perfect for this.
Yeah, let's walk through that. A LinkedIn profile. So I'm the user. That's one row in a user's table. Easy.
So far, so good. But you've worked multiple jobs. You went to a couple of different schools. You can't just stuff a list of 3 jobs into a single cell in the database.
It violates the rules. The database wants every cell to have just one single value.
Correct. So to save your resume in SQL, you have to shred it.
Shred is such a violent word for saving data.
Yeah, it feels violent when you write the code. You literally tear your beautiful object apart. Your name goes in the user table, your jobs go into a completely separate positions table, your degrees go into an education table.
And they're all linked with these ID numbers, these foreign keys. So my one single object is now scattered across 3 or 4 different places.
Yes, and when you want to look at your profile, the database has to run around, find all those little shredded pieces, and glue them back together. We call that a join.
And joins are expensive, right?
They cost CPU, sure. But more than that, they cost developer sanity. You're writing these complex queries just to rebuild something that was already one nice object in your code. It's messy.
And that mess, that friction, that's what gave birth to the challenger, the document model.
Or, as everyone calls it, NoSQL. Which is a terrible name, by the way.
I heard it was just a Twitter hashtag for a meetup.
It was. It was never meant to be a technical term, but it stuck.
But the philosophy behind it is what matters. If SQL is about shredding your data to fit a rigid structure, the document model is about accepting the data as it is.
That's a great way to put it. Document databases like MongoDB, they use JSON. It's a tree structure. You have your user, and right inside that user object, you just have an array called positions. You don't shred it. You keep the whole resume as one document.
Which immediately solves the shredding problem.
And it gives you this huge performance advantage called locality.
Okay, what's that?
Storage locality. So in the relational world, your user info is here on the disk, your jobs are over there, your education is somewhere else entirely.
So the diskette has to jump all over the place to collect the pieces.
Right. But with the document model, it's all in one continuous blob. You just say, give me user 251, and boom, the database hands you one thing, everything you need. It's drastically faster for that use case.
Okay, that sounds way better. But the debate goes deeper. The notes talk about schema on write versus schema on read. This feels like the real ideological split.
It is. Think of it as a strict safety inspector versus a free market. SQL is schema on write. You have to define your table structure up front. This column's a number, this one is a date.
And if you try to put text in the date column, it yells at you.
It throws an error. It protects data integrity. It stops garbage from getting in, which is great, but it's rigid.
What do you mean?
Well, what if you want to change that structure? Say you want to split a name field into first name and last name. You have to run a migration on the whole database. That can take hours, maybe even require downtime.
And document databases.
They're schema on read. The database basically says, give me whatever, I don't care. You can save one user with a name field and the next user with first name and last name fields. It just takes it.
But wait, if the database doesn't enforce any rules, doesn't that just push the mess into the application code? It sounds risky.
You hit the nail on the head. People say these databases are schemaless. That is a lie.
Okay.
There is always a schema. The only question is, who enforces it?
Right.
In SQL, the database enforces it. In NoSQL, your application has to be smart enough to say, okay, does this user have a first name field? If not, I better check for the old name field.
So you're trading database rigidity for application complexity.
Precisely. You're moving the problem. And that flexibility is amazing for getting started quickly, but it requires a lot of discipline from your developers.
Okay, so document models match our code objects better. They're faster for fetching whole objects. Why didn't they just completely kill SQL? Why are we even having this debate?
Because eventually, data stops being a neat little tree. It gets connected, it gets tangled, and that is where the document model starts to fall apart.
The many-to-many problem.
Exactly. Back to our LinkedIn example. In your resume document, it's easy to just type the string Microsoft as your employer.
Be simple.
Too simple. What happens if Microsoft rebrands? Or you want to show the company logo next to the name. The logo isn't part of your document.
Oh, I see. You'd have to go find every single person who ever worked at Microsoft and update the text in their profile. That's a nightmare.
It's chaos. Duplication is the enemy. So you do the sensible thing. You create a separate company document, and in your profile, you just store the company ID. But now, wait for it.
We're back to doing joins.
We are back to doing joins. We're simulating the very relational concept we tried to run away from.
And document databases are not good at joins.
They're terrible at them. The database usually can't even do it for you. Your application has to. It fixes the user, sees company ID 123, and then your code has to make a second trip to the database to ask for that company's info.
So it's slower and more complex. It gets even worse with something like recommendations, right? I write a recommendation for you. It shows my name and my photo on your profile if I change my photo.
Your profile has to update instantly. Everything is connected to everything else. And that beautiful self-contained document model just crumbles.
You know, this is where the research just dropped a huge history bomb on me. We think this SQL versus NoSQL thing is new. It's not. We have been here before.
We are absolutely repeating history. In the 1970s, the main competitor to SQL was a hierarchical model from IBM called IMS.
Which was basically the 1970s version of a JSON document store.
Structurally, yeah.
Yeah.
Nested records, great for trees. But it had the exact same problem with many-to-many relationships, so they tried to fix that with something called the network model.
And that used pointers, right? Like a direct link from a person to their company.
It did. It sounds efficient, but querying it was a nightmare. You had to literally tell the computer the exact path to take through the data. Start at the root, follow this link, turn left at this record, follow that pointer.
That's like giving someone driving directions instead of just an address.
It's exactly that. And if the data on the disk was reorganized, your code broke. Your directions were wrong. Developers were constantly rewriting their queries.
Which is the perfect lead-in to why SQL really won. It wasn't just tables. It was this shift from imperative to declarative.
This is the single most important concept in this whole deep dive.
Let's unpack that. The source used a CSS analogy that I loved. But first, what's imperative?
Imperative is telling the computer how to do something, step by step. Think of trying to change a web page with JavaScript. You write a loop, get all the paragraphs. For each one, check if it has the class selected. If it does, change its background color to blue.
You're micromanaging the process.
You're micromanaging. That's what those old databases did. You had to navigate the access path yourself.
Okay, now contrast that with declarative.
Declarative is just CSS. You don't write loops. You don't tell the browser how to find things. You just write a rule. Yeah. Selected background blue.
You just state what you want the end result to be.
You declare the result. You don't care how the browser does it. The browser's engine figures out the most efficient way to apply that rule.
And that is exactly what SQL brought to databases.
Yes. When you write select from users where location undone, you're not telling the database to scan every row. You just say, I want the users from London.
And the database has this brain inside it, the query optimizer.
Exactly. The query optimizer looks at your request and decides the best way to get it. It might use an index. It might scan the table. It might change its strategy tomorrow if the data gets bigger. Your code doesn't have to change.
That's incredibly powerful. It completely hides the complexity of how the data is stored.
That was the breakthrough. That is why SQL dominated for 3 decades.
Okay, but even SQL starts to choke when the connections get really complex. We're talking social networks, fraud detection.
It does. A few joins are fine. But if you want to ask, find friends of my friends who live in the same city as my former colleagues.
My brain hurts just hearing that.
In SQL, that's a mess of joins. And if the path has a variable length, like find anyone connected within 5 steps, SQL is just terrible at it. You have to use these horribly complex things called recursive common table expressions.
Which looks like a logic puzzle.
It's verbose, it's slow. And that brings us to our third contender, the graph model, for when the relationships are more important than the data points themselves.
So if relational is tables and document is trees, what's a graph?
Think of a whiteboard. You draw a circle, a node, and label it Lucy. You draw another one called Idaho. Then you draw an arrow between them and label that relationship born in.
Vertices and edges.
Exactly. It's a much more natural way to model highly connected data.
And the source materials example of Lucy and Elaine really shows this off.
Right. Lucy was born in Idaho, which is a state. Elaine was born in Boone, which is a town. In a relational model, that's messy. You need a towns table, a states table, a countries table.
But in a graph.
They're all just nodes. You have a node for Boone, a node for France, and an edge between them labeled Partoff, a node for Idaho, a node for USA, same thing. You can model the world as it actually is without forcing it into rigid columns.
And querying it is totally different. The source mentioned a language called Cypher.
This is where it gets really cool. In Cypher, the query language for Neo4j, your query looks like ASCII art.
ASCII art? You're kidding.
I'm not. You literally use dashes and arrows. To find where Lucy was born, you write a pattern that looks like %spornen location. You're drawing the pattern you're looking for.
So for that crazy query, find people who emigrated from the US to Europe.
Graph databases eat that for breakfast. Because for them, a join isn't something they have to calculate at runtime. The relationship, that pointer, is physically stored. They just follow the arrows. It is lightning fast for that kind of problem.
What about triple stores? The notes mentioned those. Is that the same thing?
Same family, different philosophy. Triple stores came from the semantic web idea. They break everything down into subject, predicate, object. Jim likes bananas.
It sounds very academic.
It is. The dream that the whole internet would be structured this way didn't really happen, but the model is still incredibly powerful for certain kinds of data.
So after touring this whole landscape, relational, document, graph, who wins?
You know the answer to this. It's the answer everyone hates.
None of them.
None of them. Or all of them. It's always about the trade-offs.
There is no silver bullet.
Never.
Okay.
If you're building a blog, use a document database. If you're building an invoicing system, use a relational one. If you're building a recommendation engine, use a graph.
And in the real world, big systems use all of them together. This polyglot persistence idea.
Exactly. A single Uber trip probably touches a dozen different databases. A key value store for your real-time location, a relational database for the billing, and a graph database for the road network. We've stopped looking for the one database to rule them all.
But before we wrap, the source left us with this really provocative idea. We've talked about these 3 big models, but they aren't the only ways to see the world.
Not even close. We've barely scratched the surface.
The example was genome research.
Right. DNA is just one giant gigabytes-long string of letters. If you want to find similar sequences, not exact matches, SQL is useless. Graphs are useless. They had to invent completely new kinds of databases, like GenBank, just for that problem.
Or particle physics at the Large Hadron Collider. Petabytes of data.
They're not thinking about foreign keys. They're thinking about how to write data to disk fast enough so the buffers don't overflow. Their solutions look nothing like anything we've talked about today.
Which brings us right back to Wittgenstein. The limits of my language mean the limits of my world.
It does. If the only tool you have is SQL, every problem looks like a table. If you only know JSON, every problem looks like a tree. The future isn't just picking the right model off a shelf.
It's realizing that sometimes we have to invent a new language to describe a new world.
That's it.
That's a thought to chew on the next time you write a line of code. Are you building the model, or is the model building you?
Deep.
We try. Thanks for taking this deep dive into the hidden structure of our digital world.
It was a pleasure.
See you next time.